So here we saw the inclined distance, how to calculate. So it is only one more component will be added, which is the elevation. So this is the elevation. Now we can see how to solve the problems. So the first problem here is with respect to the scales. A vertical photograph was taken from a height of 1850 meter above the MSL. So determine the scale of the photograph for an area at average elevation of 275 meters above the MSL. And focal length of the camera is 15 centimeter. So here the height is given, that is 1850 meter above the mean sea level, and h is the uh, height above the MSL, so that is 275 meters, and focal length is 50 centimeter. And scale, we saw the formula just before. So here it is the datum scale, so f divided by h minus h. So that is f is your focal length divided by the height of the aircraft, and this is the height of the ground level above the MSL. So if we work out, the scale is found to be 1 by 10,500. And the second problem is the inverse of the first problem. So here a camera of a focal length at 20 centimeter is used, focal length is given, and the average elevation of the terrain is 1900 meters. And at what height the aircraft should fly so that the scale of 1 by 10,000 can be maintained. So focal length is given and the terrain height is given. So we need to determine what is the height at which should aircraft should fly so that the scale is maintained. So focal length is given, scale is given 1 by 10,000, and the height above the mean sea level, that is 1900 meters ground elevation, that is given. So capital H is the only unknown. So if we substitute, we get the value as H is equal to 3900 meters. And the third problem is related to the distance, calculation of the horizontal distance and the vertical distance. So here a vertical photograph is taken from a height of 3200 meter above the MSL with a camera of a focal length 120 mm is given. So it contains two points A and B, uh, which is corresponding to the small a represents the points on the photograph and capital A represents the points on the ground. Now we need to calculate the horizontal distance AB as well as the average scale of AB, because the elevation is varying in this terrain, and we also need to find out what is the inclined distance. So the table is given, so photo coordinates, the corresponding ground elevation, and your x and y on the photograph is given. So here it is like your principal plane only. So you have your photograph, principal plane is there. From the principal plane, what is the point where the point is located? So it is similar to your Cartesian coordinate system. So let's see how we can solve this. So we, from the scale concept, we have seen how we can find the coordinate on ground. So first step in this problem is to find out what is the coordinates on the ground. So for the point A, xa is equal to h minus ha divided by your focal length into your photo coordinate. So you will get your capital XA, and similarly for YA also you can get the capital YA, and for xb and yb. So this also you will be able to find. Now once we apply the distance formula. This is the horizontal distance, xa minus xb the whole square plus ya minus yb the whole square, and we can find out what is the horizontal distance. And in the vertical distance, another component is added, that is the ha minus hb the whole square, and we can find out what is the uh, inclined distance. Now we need to find out what is the average scale also in this question, that is f divided by h minus h average. So if you take the average of the given elevation and then substitute in the formula, you will get average scale as 1 by 20,750. So this is the first three problems. Now let's go to the concept of relief displacement. So relief displacement I have already taken in the first week. So now I will show you how to derive that. So let us say this is our exposure station, and let's say this is the positive plate of your photograph. Now we have our tower. So let's say this is the tower. So the top point of the tower and the bottom point of the tower, so they both are in line with each other, and this is the height of the tower. Now the sensor is capturing the image. So your top of the tower will come like this, and your bottom of the tower will come like this, and it intersects on your photo plate. So this is the bottom of the tower point, top of the tower point. So let's say this is capital R naught. So this is R and this is R naught, and let's say that this is at a distance of so let's say that is A and A naught, and this is at a distance of capital R from the principal axis, and on the photo plate also you can see. So let's say that this is at R naught, and this distance is at small r. And this is the focal length, and let's say that this is the height at which the aircraft is located, and from the top of the tower, so this height is nothing but your capital H minus H. Now we are going to use the concept of a similar triangle. So the first triangle that I'm going to take is I'm highlighting it with the pink line. So that is the first triangle, and the second bigger triangle is this triangle. So both the triangles will look something like this. So this is the bigger triangle, and within that there is a smaller triangle, and this distance is R naught. This is F. This distance is H minus H, and this distance is capital R. So this is one triangle, and the second triangle I'm going to locate it with the blue line, and I'm going to shade that. So this is the second smaller triangle, and the bigger triangle is the entire. So this is not R naught, so this is R. So if I draw the second triangle, so this is again F, but this height is capital H. Now this is R naught and this is R. Now I'm going to write the similar triangle equation. So F by H minus H should be equal to R by R. Similarly for this, F by H should be equal to R naught by R. So from both this, R is common. So I'm going to write equation for R. So R is equal to H minus H into R divided by small f from the first equation, and from the second equation R is equal to H into R naught divided by F. So since both are same, I am going to equate both. So here F is common, so I can cancel that out. Then if I write, the remaining will be HR in HR minus HR. So here capital H is common, so we can bring it to one side. Minus capital H into R naught should be equal to H into R. So if I take H common, this is R minus R naught into HR. So R minus R naught, that is the relief displacement. So if you see on the photo, the top and the bottom point of the tower. So this is the top of the tower, this is the bottom of the tower. So they both should be ideally at the same place, but here it is shifted by a distance R minus R naught. So that I'm going to call it as a small d. So H into d is equal to H into R. So we need relief displacement. So HR divided by capital H. So this will be your relief displacement. So this is how you will derive the relief displacement equation. So that is what I have derived, but this part unfortunately did not record. So I have derived it again. So next is the problem related to the relief displacement. So here problem 4, section line AB 300-meter long on a flat terrain measures 102.4 mm on the vertical photograph. A radio tower also appears on the photograph. The distance measured from the principal points to the image of the bottom and top of the radio tower was found to be 7 centimeter and 8 centimeter. So the distance from of the top of the tower and bottom of the tower from the principal point. So that is your R and R naught is given. So you'll be able to find out what is the relief displacement. And the average elevation of the terrain is 553 meters. Determine the height of the tower. So here focal length is given to be 152.4 meter. So in this question, if you see the height at which the aircraft is flying, that is not given. Instead, one more data is given. So 300-meter on a ground is equal to 102.4 mm on the photograph. So this is like a kind of equivalency factor. So using this, we can determine what is the scale of the photograph first. So R is equal to 300-meter on ground, and on photograph it is 102.4 mm, and we can find out the scale. R by R is equal to the scale, so that is given. Now we have a tower, and a similar concept I have just drawn it here. R1, R2 is given, and relief displacement is 8 centimeter minus 7 centimeter, that is 1 centimeter. And we can find out what is the relief displacement. Then we need to find out what is the height of the tower. That is nothing but your small h. So with the relief displacement, we will substitute in that, and then we come to know that height of the exposure point is not given. So we need to find out the capital H. So we know the scale, and we know the formula for scale also, and average elevation is given. And here the only unknown is your capital H. So your capital H is equal to 999.48 meters. Now we need to determine the small height, sorry, the height of the tower, which is the small h. But this height is associated with respect to your mean sea level. Now, since we need to find out the height above the base of the tower, so we need to subtract that effect. So our relief displacement formula, d is equal to h into r divided by, it should be actually capital H, but since we need to find out with respect to the base of the tower, I'm going to subtract that h average of the terrain. So your relief displacement is 10 power minus 2 1 centimeter into h into r is the top of the tower, 8 into 10 to the power minus 2 divided by h is 999.48 meter minus 553. So from this we can estimate the height of the tower to be 55.81 meters. So your next topic is related to the stereoscopic parallax. So that is your parallax error. So in parallax error, so whenever a survey is being taken, you will have multiple exposure. So let's say that this is your flight direction. And you have one exposure station here, and your second exposure station is here. So I'm going to mark it as E1 and E2. And the distance between these two exposure station is called as the length of airbase. So length of airbase, it is represented by the letter B. And exposure station 1 has a positive plate, and exposure 2 also has a positive plate. And you have a tower on the ground. And your MSL is somewhere here, datum. Now let's mark the relevant factor. This is your capital F, this is your capital height, capital H, this is height with respect to the bottom, this is height of the tower with respect to the top of the tower, This is your first principal plane, second principal plane. Now, from the first exposure, we can capture it will capture the top of the tower. So let's say it has captured. And in your second exposure, it will be onto the left of the principal plane. So this is the point capital A, this is the point small a on the first photograph. This is your small a on the second photograph. And this is at a distance of x1 from the principal plane, and this is at a distance of x2 from the principal plane. Now what we are going to do is we are going to locate the point A1 on exposure to photo. So if we do that, so it will be somewhere here. So this is the point from A1 first photograph, and this distance is going to be x1. So with respect to your first exposure and your second exposure, your top of the tower has moved by a total distance of x1 plus x2. So that is your parallax of the top of the tower. Similarly, if you draw the same thing with respect to the bottom of the tower, you will get a similar point, and that distance x2 plus x1 will be equal to the parallax for the bottom of the tower. So now we can derive the equations. So again, it's going to be the same similar triangle concept. So first one is triangle E1A E2, and the second triangle is E2 A2 A1. So from this, if we write P top by length of the base is equal to F by H minus H top. So we need P top. So P top is equal to F into B divided by H minus H top, and P bottom is equal to F into B divided by H minus H bottom. Similar equation. Now we can solve one problem related to the parallax. So that is the fifth question. A tower appears in two successive photographs taken at an altitude of 4000 meter above the ground level. So your capital H is given, and the focal length of the camera small f is given, and length of the airbase is 300 meters. The parallax for the top and the bottom of the pole. So your P top, P bottom is given. Now what is the height? So we need to determine what is the height of the table, height of the tower. So you have the equations. It is just a direct application. So once you understand the concept, you can derive the equation by yourself. So you just need to draw the diagram. So this will be problem 5. So your capital H is given as 4000 meters, and focal length is given as 160 mm, and length of the airbase is given as 300 meters. So P top is 72 mm, P bottom is 63 mm. So you just need to substitute and then you need to find out H top, H bottom, subtract both, you will get the height of the tower. So I'm going to write it for top. 72 is equal to 160 into 300 divided by 4000 minus H top. Then this will be P bottom. So H top minus H bottom. So that is 95.23 meters. And the next concept is related to your number of photographs required. So whenever a survey is being conducted, uh, n number of photographs will be taken, and these photos will be taken such that they overlap with each other to a certain extent. So if this is the first photograph, so this is the flight direction, and your second photograph will be captured like this. Then comes your third photograph. So this region which is overlapping in along the flight direction, that is called as a longitudinal lap. And once it goes to a certain extent, your flight is going to so if your flight is going, this is the center line. After it goes, it turns back and then captures the goes into the next flight line. So when it comes this side, the second part, so it is going to overlap on your first photograph as well on the sides. So you are going to have side lap. So this is called as side lap. Now let us say PL is the longitudinal overlap, that's in fraction. PW is the side overlap. And L is the ground length. W is your ground width. So your capital A, that is L into W, is the area. Your small l, length in photograph. So that is your length of photograph. and your small w is the width of photograph. Let's say your small a, that is small l into small w, that is your area in the covered by the photograph, and let capital S be the scale. Now the effective length that is captured by the photograph. One photograph. So that is your capital L is equal to 1 minus percentage of the longitudinal overlap into scale into your length in the photograph. And similarly, your capital W is equal to 1 minus PW into scale into small w. So you don't have to remember this, just you need to remember the concept. So we are converting the photograph dimension to the ground dimension. For that we are multiplying it with the scale, and since it covers only the since there is a longitudinal lap, it covers only effectively a reduced length, so that is PL. So if it is 70% overlap, then you can effective length that is covered will be zero point 0.3 only. So 70% overlap is there. Now we can find out what is the ground area covered by photograph, that is your L into W. So capital A is equal to L into W, 1 minus PL into SL into 1 minus PW into SW. So that will be A is equal to 1 minus PL into S square into LW. So now number of photograph required. Area on the ground divided by area covered by the photograph by one photograph. So first we need to calculate what is the number of photograph required in the longitudinal direction. So that will be length on the ground divided by effective length covered by the photograph on the ground plus one additional photo, because your flight is let's say this is the entire study area. So what it will do is, here also you will have one more flight path. So it would have come, so this is your first path, then you would have taken a turn, then this is your second path, then here it would have come, then this is your third path, and you come this side, and then fourth path. So you will have one extra photo on either side. So if it is given on either side, extra photo is given, you should add another plus one. If it is only one, one side, then you can take you can just add only one, not two. So one side, this is for one additional flight line. If it is having two additional flight line, then you add plus two. So similarly, number of photos on the width, that will be 1 divided by EW into SW plus 1. Now total number of photographs will be longitudinal side and your width. So that will be your total number of photos. And there is one more thing. What is the interval between two exposures? So this is nothing but time interval. So you know the what is the distance of the air base, and you know what is the flight velocity. So if you divide this, you will get your interval between two exposures. Now let us see one problem related to the exposure, number of photographs and the exposure. So an area of 10 by 20 kilometers to be surveyed using the aerial photogrammetry. So this is your ground area that you need to cover using aerial photogrammetry. Average scale is given. So your small s that is given at a ground elevation 400 meters above your datum. Focal length of the camera f, small f is given, and size of the photograph. So this is your um, coverage of one photograph, and speed of the aircraft is given as 270 kilometer per hour. Longitudinal lap is 70% and side lap is 30%. So now we need to determine what is the flying height, exposure interval, number of photographs required to complete the survey. So we can see how to solve this question. So your size of the photograph is given as at 23 centimeters by 23 centimeter, and scale is 1 by 10,000, and h average elevation of the terrain is 400 meters. Longitudinal overlap is 70%, side overlap is 30%. Your velocity is 270 kilometers per hour. So I'm converting it into meter per second. 270 into 5 by 18. That is 75 meters per second. And the focal length is given as 20 centimeters. Now first we need to determine what is the flying height. So that is related to your scale. Scale is equal to f divided by h minus h average, which implies your scale is 1 is to 10,000. This is 20 into 10 to the power of minus 2 meters divided by h minus h average is 400 meters. So if you solve this, your flying height is around 2400 meters. Now we need to determine the exposure interval. And for that we need to estimate what is the ground distance between two exposures. So your length between two exposures. So L is equal to 1 minus PL into SL. So L is equal to 1 minus zero point 0.7 into your scale is 10,000. So this should be into your small L is the length of the photograph, that is 23 centimeters. So your length, effective length that is actually captured by one single photograph is 690 meters. So after 690 meters, there will be another photograph. So this is your length of the airbase. Now we can find out the exposure interval. 690 divided by, that was 75 meter per second. So this is around 9.2 seconds. So for every 9.2 seconds, there is a photograph that is being taken. Now we need to determine what is the number of photograph on the longitudinal side. So that is distance covered on the ground. So your study area is 10 kilometer by 20 kilometers. Your capital A is 10 kilometer by 20 kilometer. So let's say this is 20 kilometers and this is 10 kilometers. So this is the direction of the flight. So that will be 20 kilometers on ground. And what our camera is actually capturing? So our camera is actually capturing 1 minus longitudinal overlap multiplied by, you are going to scale up the distance 10,000 multiplied by your length of the photograph, that is 23 centimeter plus 1. So this will be equal to 13.42, that is approximately 14 photos. Similarly along the width side, so that is 10 kilometers, and it is having a 30 percentage of overlap, 1 minus zero point 0.3. We are going to scale it up, so 10,000, and distance is 23 into 10 to the power of minus 2 plus 1. This is 15.81, that is approximately equal to 16 photos. So the total number of photos will be NL into NB, that is 14 into 16. So that is 224 photos are required to complete this survey. So this scale which I have mentioned in the formula, that is ground to photo. So distance on ground divided by distance on the photo. That's why we are applying 10,000 here and not 1 by 10,000 in the problem. So we are scaling up our photograph dimension to the effective ground dimension. So that's why this ratio is 10,000. Okay, this is all about your photogrammetry. Now I will demonstrate to you the histogram equalization. So I am giving some additional problems. You can work it out on your own. So these three problems are additional problems. Okay, let's go to the histogram equalization demo. So here if you see the left hand side on the top is the surface reflectance of Landsat 8 band 2 data, and this runway is the Chennai International Airport before histogram equalization, and this is after histogram equalization. So now I will show you the demo of how to do it. So I'm opening with QGIS. Okay. So first I'm going to load the data. So this is our surface reflectance band 2 data. Now first we need to get what is our uh, histogram. So for that, go to raster, miscellaneous, raster information. So first we need to get the histogram. So in the advanced parameters, type hyphen HIST and then run this. So now if you see here, let me do it in another version. So I'm typing hyphen hist and then I'm running it. So you are having 1,000 buckets from 46 to 33959.9. So I want to copy this data. So I have already done that. So from that, what we need to do, we are reducing our dimensions. So we are taking the lower bound and the upper bound from the histogram that is generated, and then number of buckets we are fixing, and this is the difference between upper bound minus lower bound divided by number of buckets. So we will get what is the incremental value for each bucket, and this value is the lower bound value plus the bucket size, that is the first value, and we need to add it up until the end. And what we are doing is we are finding out this data we will get from the QGIS, the raster information. So this is the frequency. So this data, this is the frequency that we copy paste, and this is then we need to find out what is the summation of that. So this many number of pixels are there, and then so this is 2 divided by the total number of pixels. You will get the probability, and then you can find out what is the cumulative probability. So this is the previous probability plus the current probability. Then you can multiply. So we are stretching, we are going to change. Currently it is in 16-bit, we are going to the 8-bit data. So we are going to equalize it between 0 and 255. So we are going to multiply our cumulative probability multiplied by our new upper bound minus new lower bound, and we are rounding it to the nearest integer. So if we do that, we will get the values between 0 to 255. Now once we do that, our lower bound is the actual lower bound, and the for the first interval the upper bound is this value. So that is the new upper bound, and this is the mapped values. So similarly for the second interval, the upper bound of the previous interval will be the lower bound, and this second value is the upper bound of the second interval. So this will be mapped to the new upper bound, and here you have the new value. So you need to take this. You can copy this, and then you can paste it in a new folder, a new file. So we will export that to your QGIS. So the template is, your first row should be your lower bound, second row should be your upper bound, and third row is your new value. And we need to save this as a CSV file. So I have already done that. So I am going to open that in the QGIS. So open delimited text. So this is the CSV file .csv. We need to open that, and here you need to select a no geometry. So it will get added as a table. So here this is the table. You can right click on it, open attribute table, you will get the values. Now here we need to type reclassify by layer, and then you need to select the raster layer and the table containing the class break. So this is the table which we imported. Minimum value is the lower bound, maximum value is the upper bound, output value is the new value, and range boundary is minimum less than value less than or equal to maximum, and output data type we need to change it into 8 bit, that is 1 byte, and then you need to click on run. So now we can see the histogram equalization has been applied, and your image is enhanced. So the edges of the runway is now more clearly visible than the blue band data. And like this you can do it for your own data. I have shared this data as well. You can try it out on your own. So this is with respect to the histogram equalization. I think now it is Now you know how to do it. So next is the unsupervised classification. So I have a small study area. So in this, we are going to see how we can use QGIS to do the unsupervised classification. So I'm going to demonstrate how we can perform, and this is one of the output which I generated yesterday while checking whether it is working or not. So we will do the same data set now. So I have the QGIS open. So let's say we can do it for the data set. So I will load the data set. So this is atmospherically corrected Sentinel-2 data. These are the bands which I have used. Like in last class also I have used the same image. Okay. So now to do the unsupervised classification, so I have just imported the Google Earth reference. So this is the area for which we calculated the NDVA, NDBA and so on. So I have just imported all the bands. So I'm going to remove the Google because we are going to create a band set. So go to SCP band set. So once you come there, this window will be loaded. So if you just click on this refresh list, so whatever is the raster that is open on the left side will be displayed here. So this is the band set that has come. So now if I click the plus button here, so first I need to select everything. Click on the plus button, it will come here. Now here we need to set the wavelength. So here it is Sentinel-2 band. So I am setting the Sentinel-2. So the central wavelength for all the bands has come automatically. Once this has come, so this is band set 1. Now go to the band processing. Here you can see an option called as clustering. So click on that. So this is the unsupervised classification window. So our input is the band set 1 and the distance threshold. So this is the different thresholds. So like if you are doing unsupervised classification in parallel pipe, I told you can take 1 sigma, 2 sigma, and it will, with respect to the mean, it will move to the left or the right. Similarly, in the k-means cluster also, we are taking x minus mu. So we can set this distance threshold. It's an iterative process. So I'm going to go with the default for the demonstration purpose, and I'm going to have only 5 number of classes, and number of iterations I'm going to keep it as 10 itself. So but just for demonstration I'm keeping it as 10, but to get a reliable results you need to at least give 20 iterations. And here you have two methods, k-means and isodata. I'm going to demonstrate k-means. So this two inputs doesn't mean anything if you are doing the k-means clustering, and use the no data value as 0. Now it is a repeated process, so you need to like do multiple iterations, adjust the distance threshold until you get your reliable results. So here if you see, we are not giving any training pixels, so we are just going to classify it and it's going to give us the number of classes. So I'm going to save it as classification 1, save, and now it is running in the background. So it is going to run 10 iterations. So now it has done. So here if you see, it has created 5 clusters, and this is the spectral signature and the corresponding distance. So this we can see later for our analysis. So now we can see our output, how the output is. So I'm removing all the other bands, and then I'm going to bring in the Google Earth. Let's see how it has classified. So if you see, 0 is unclassified, so we have some 0 pixels also. So one, cluster 1. So now it has given us the different clusters. Now we need to correlate with our ground truth data, and then in this case we are seeing the Google Earth map in the behind, and we need to assign the class. So it has just given these are all the same clusters. Now we need to assign the class manually. Let's say if I just remove this green, if I say it is agricultural land, so class 1 is agricultural land, and then if I go to dark green, so it is like a barren scrubland kind of. Let's see here. So it is another type of maybe a different type of crop which is having a spectral different spectral signature. So if you see here, the crops are different. Here the crops are different. So maybe this is another type of crop. And what is number 3? So number 3 is here. So number 3 is another type of agricultural land. If you see here, the cropping pattern is different, more dense. And let's go to number 4, brown areas. So this is the river bed. And number 5, these are light red. So these are dry agricultural lands, fallow lands. So like this, we need to see one by one and then assign the classes by ourselves. And if you see here, this water body and agriculture has become one single cluster. Maybe because when this image was taken, the water was less in this particular water body. And if you see here, there are so much of algal blooms. So this also gives the spectral signature similar to your vegetation. That might be the reason why this has come as a one single agricultural cluster. So that could be one of the reasons. So you need to do repeated iterations to get a perfect result. So this is how you do unsupervised classification in QGIS. So very simple, but you need to do number of iteration. You need to fine tune it to get a reliable result. So let's say that once you get your classification done, let's say this image is taken for 2005, same place you take it for 2010, and you want to see what are the changes that has happened. For that is the change detection algorithms. So your first image is maybe 2005, and this may be 2010, and you are going to see what are the changes. So it is going to compare pixel by pixel, and then it is going to give you what is the change. So why it is important? You need to see what is the growth of the urban area, or if you want to see if the water body has disappeared. So this kind of studies you can make use, you can do it in by using the change detection method. So I'm going to show the demo. This is for the Pune city. So the first land use is between 2004 to 2005. Second land use is 2014 to 15. So 10 years gap. You can see the from the land use itself. So red pixels are your urban area, and yellow pixels are your agriculture, fallow, forest, and brown is your barren lands, and blue is your water body. So you can see how much difference has taken place in the urban part, how much the urban area has grown in just 10 years. So we are going to estimate that. So once you do the change detection in QGIS, it will result in a map like this. So you can see what are the classes that has been converted into some other class. So blue means fallow to built up, plantation to built up. So you can see which pixel has converted into which land use. And this change detection will be affected severely by your classification accuracy. So if there are a lot of mixing pixels and your accuracy of the classification is less, it will be directly propagated into the change detection also. It will give you unreliable results. Say your water has your built up area has converted into water body. So this is like very unrealistic change. So these are some of the things which you need to keep in mind. And once we do the change detection, we need to arrive at a inference something like this. So this is your reference class, your first land use, and this is your new class after 10 years. So your agriculture has become built up. So that is what this means. So old ID is agriculture and new ID is built up. And how much is the area? And we can calculate what is the total area. So increase in the urban area for Pune over the decade is 315.49 square kilometers, and increase in agriculture is 18.06. Increase in the wasteland is 187.35. So this kind of inferences you can make from the change detection. Now I will quickly demonstrate how to do that in QGIS. So I'm removing both the datas and I'm going to input the change detection. So this is the LULC for 2004, 2005, 2014-15. And one thing which you need to ensure is both the images should exactly overlap with each other. So there should not be any mismatch. So for that you need to do the image to image rectification. That is the part of your geometric correction. Only then your pixels will be correlated. So to do the change detection, you go to the SEP tool, go to post processing, and if you see land cover change, so that is the change detection. So your reference classification is the old data 2004 2005, and your new classification is the after 10 years. And report, I don't want to report unchanged pixels, so you just select this two and then you can run it. So now you need to save the change map. So it will go pixel by pixel, it will compare which pixel has converted into which pixel. So this one is completed. So I will just remove both the things. So you can see what are the change. So it has given many number of pixels. So if I go to symbology unique values, so it has given me 49 different changes. Now I need to see what are these changes actually. So if I go to the place where I did my change detection, there should be another. So this is the change.csv. So I'm going to open that in the Excel. So data, text to columns, space. So I'm going to remove all the double colons and replace it with this so that we can copy and paste it in our Excel. So you can see. So this is the numerical output 1 to 49 and the new class ID reference class. So reference class is 2004 to 2005 and new class is 2014 to 2015. So how many number of pixel and what is the corresponding area in meter square. So from this one means maybe urban is urban. So there is no change. Then if you see here, agriculture has turned into urban. So this much amount of area. So some of these pixels, you need to analyze this result. Then you need to remove some of the things, and then you need to filter out. So here you have the land cover change matrix. So this you need to, yeah, this also you can check. So you are when you narrow down everything, this is the kind of output you will get. So this is the reference class. This is your reference class. This is your new class. One. All your principal diagonals are no change. Then rest of the off diagonals will be your change. So if you see, first pixel has changed into uh, second pixel. So that kind of changes you can monitor from this, and you will be able to arrive at this table. So that is what the change detection is. Now I'll quickly give a very quick intro about the microwave remote sensing. We will cover this in greater detail in the upcoming sessions. So first, why microwave is being used? So microwave is independent of solar illumination. So whether you have a source of electromagnetic radiation or not, you can do it in the active mode. And for passive mode, you need the sun as the source of light, electromagnetic radiation, and it is independent of day or night. So you can do it at any time, and it has both imaging and the non-imaging modes. And most important thing, it has the all-weather capability. So it can pass through clouds, which is one of the most biggest disadvantage of the optical remote sensing. So if there is a heavy rain happening over the area and you want to see what is happening on your surface, so you will not be able to use your optical remote sensing at that point, because all you will see is only clouds. But microwave has the ability to penetrate the clouds for certain bandwidths, certain wavelengths, and you will be able to see what is happening on the ground. And here we have the control over the electromagnetic radiation source in case of the active mode. So our input power, frequency, polarization, all this can be changed. And we can also control the imaging geometry. So we can adjust our altitude, we can adjust our look, we can adjust the depression angle, and we can get our own custom images. And key difference when compared to optical is optical remote sensing just tells you about what is the surface layer of the imaged objects. But in microwave remote sensing, we can know about both the geometric as well as the dielectric properties of the surface. So we will be able to see what is the kind of surface that we are dealing with and its electric properties, because we have the polarization component. We will see what is polarization in the later sessions. And since microwave is penetrative in nature, we can able to get the subsurface features also, only to a certain extent, but we will be able to get a little bit. And it also provides complementary information to the optical remote sensing. So whatever the things that we are not able to do with optical, we can do with microwave remote sensing. So if you see our electromagnetic spectrum, so the shaded portion are your absorption areas, and the blue areas are your atmospheric windows. So your microwave region is somewhere here. So that is from let's say 5 centimeter almost to about 10 meters. So you can see you have a very clear window. There is no absorption. So which means we will be able to look beyond the clouds as well. So this is an example, optical image of the same area. There are so much clouds in the optical image, you will be able to get, you will not be able to get any information out of it. But microwave gives you some information which we can use it for our further analysis. Now, for similar to your optical bands, in microwave also you have a different bands. So it starts from Ka band, which is from almost 1 mm all to about 10 meter, which is your very high frequency band. Ka band, K band, Ku band, then X band, C band, S band, L band. So these are all the different bands. So when it comes to our purpose, we will be using from X band. So X band will be used for the meteorological. That is your if you want to analyze the cloud coverage and all this, we have the X band radar. So that will be able to give you the uh, information for the meteorological purposes. C band is what we really use for all our purposes. We use for the different application, oil spill, agricultural application. Then in agriculture, we will be looking how to find out the rice crops. And S band is more penetrative in nature, and L band is also penetrative in nature. We can even see under the surface. So these are all the different bands and their wavelengths. And if you see, this was what I was saying about Ka band. So as you move from the right to left, so your Ka band will be affected more by your is maybe affected by your clouds, but your L band is highly penetrative in nature. And here, higher the wavelength, the more will be your penetration power. So if you see here, on the left hand side, y-axis is the transmission rate, and your x-axis is the different bands. So your K band has the lower wavelength, and your S band has a highest wavelength in this particular graph. So as you move from left to right, you can see the transmission rate. So if there are some water clouds, so almost 40% to 60 percentage of your microwave will be transmitted through the cloud, and if it is a ice cloud, 100%, almost 100% is transmitted. And as you increase your wavelength, your transmission rate is also increasing, so we will be able to get a clear picture of what is happening on the ground. So this is through water laden clouds. In case of rain, your K band has only 20 to 60 percentage of the transmission rate, and as you move further away, You can see in the C band is almost 80 to 100% transmission, so we will be able to make use of that information. If it is L band, it will be almost 100% transmission. So in active mode, what we are really doing is we are detecting, locating, tracking, and recognizing the objects. So how we are doing it? We are doing it by the principle of measuring the range. So your transmitter will send a pulse towards the target with some input power. Let's say it will be in some kilowatts, 1,100 kilowatt, or something like that. It will send a pulse. It will travel towards the target, hit the target, and the target will reflect back the pulse at a much lesser power. It will be in the order of milliamps or something like that. And the time taken to receive the return pulse is noted. So we know what is the distance to the target. We know what is the time that is taken for the pulse to return back, and we know the velocity at which it is traveling, and we can determine what is the distance. So your distance is nothing but your range, 2D, and if you speed is equal to distance by time, so the same concept is being used here. So it is ct by 2. So you will be able to say what is the exact distance at which the object is located. So here you have two types of radar. One is the monostatic radar and another one is the bistatic radar. So your if the radar is transmitting a signal to the target and it is receiving the signal back, it will be operating in the both transmission mode and also in the receiving mode. So then it means it is monostatic radar. In bistatic radar, you will have two separate radar. One is the transmitter and another one is the receiver. So this bistatic radar is being used. So mostly for remote sensing purposes, what we will be using is we will be using the monostatic radar. So it will act as both transmitter and the receiver. So today's last part of the lecture, I will conclude with this. It is too much content for one week. So this is the radar geometry. So if you see here, this is the flight path, and let's say you have the sensor here, and all our active radars are side looking radar. So it is going to look towards the one side of your flight path in the perpendicular distance, and it is going to emit your pulse. So your pulse is going to travel along this slant range, and then it's going to hit your ground. So you will have two ranges. One is the near range and one is the far range, and the width is your swath width. And if you see, the beam will not be exactly rectangular in shape. So if you say your beam is going to travel something like this, and if I draw a 3D image, so it is going to keep expanding. So this is the exposure station, and as it travels away from the sensor, it's going to keep expanding. So your actual coverage, how it will be on the ground, is in the near range you will have a some resolution, and as it moves wider you will have a higher resolution. So this distance and this distance will not be same, and as a result you will not get a square pixel, rather you will get a rectangular pixel. So let's say this will be 10 meter by 3 meter or so. So you have two different types of resolution. I will cover it in the next session, subsequent sessions. So we will see more about the radar geometry and the microwave remote sensing in the next session. So in this lecture, you just remember you have your flight path, and this is your azimuth direction, and this is your range direction. So along your azimuth direction, you have a resolution called as azimuth resolution, and along the range, you have the resolution that is a different resolution. And then you have your look angle, and if it hits the ground, you have your angle of incidence theta I. So we will see all that in the subsequent session. So thank you. I hope the demos are useful. Um, we will see in the next session.